Hello, this is Engineering Statistics and Linear Algebra 18 EC44 Module 4 Lecture 4. In the Lecture 3, we have seen how we can solve AX equal to 0. Now we will be seeing how we can solve AX equal to B. So first we will consider the algorithm for solving AX equal to B, or same thing as solving UX equal to C, and again the same thing as solving RX equal to D. The first step is reducing the AX equal to B to UX equal to C by means of the elimination method. The second step is considering the free variables as equal to 0, find the particular solution to AXB equal to B and nothing but UXB equal to C. Then finding the special solution to AX equal to 0, as in the case of solving AX equal to 0, same thing as solving UX equal to 0 or RX equal to 0 by considering each free variable in turn as 1. Then X is made equal to XP plus the different combinations of Xn with their special solutions. Now let us consider the same example which we have considered earlier, where we have considered X equal to B, that is equal to B1, B2, B3, and we try to apply the elimination method to the augmented matrix here, which is the combination of A as well as the vector B for the earlier value of A, which leads us to UX equal to C as follows. So we will get 1, 3, 3, 2, 0, 0, 3, 3, 0, 0, 0, 0 as A. X is same U, V, W, Y. Now we will have the what you call right hand side as B1, B2 minus 2B1, B3 minus 2B2 plus 5B1. And this is what we will have for the UX equal to C. U is here 1332, 0033, 0000. X is UVWY. And C is B1, B2 minus 2B1, B3 minus 2B2 plus 5B1. Now you can see that the last row is all zeros here. So therefore, this value B3 minus 2B1 plus 5B1, B3 minus 2B2 plus 5B1 should also be equal to 0 for the consistency, for the sake of consistency. Otherwise, if this is not equal to 0, then it will become, the set of equations here will become inconsistent. Whatever you are given, the set of equations corresponding to AX equal to B will become inconsistent if this condition equal to 0 is not satisfied. That is, AX equal to B can be solved if and only if B lies in the column space of A. So we are back again to the definition of the column space of A. So solution for the column space of A is possible only if the set of equations is consistent. That means B3 minus 2B2 plus 5B1, which gives us the values of B1, B2, B3. That is nothing but B, equal to this value B3 minus 2B1 plus 5B1. B3 minus 2B2 plus 5B1 should be equal to 0. This column subspace, which we have just got, comes from the 4 columns of A. Please remember that column subspace comes from the 4 columns of A rather than the columns of U. And the different columns of A are 1, 2, minus 1, 3, 6, minus 3, 3, 9, 3, and 2, 7, 4. The first and third columns are independent columns, which have the pivot variables. The second and fourth are dependent columns, which have the free variables. So these two will correspond to the, independent columns or pivot columns, and these two will correspond to the second, and the fourth will correspond to the dependent columns or the free columns, which will give us the free variables. The column space CA can be described in two different ways. We can describe the column space, which we have just written, in two different ways. One is, it is a plane generated by the column 1 and 3. We have two columns, which corresponds to the independent columns and pivot variables. So it is a plane generated by the columns 1 and 3. The other columns lie in that plane and contribute nothing new. That means the column 2 and the column 4 will lie in the plane which is generated by the column 1 and 3, and they'll contribute nothing new there. The column space can also be described by the another way, which is it's a plane of all vectors B that satisfy the condition, which is B3 minus 2B2 plus 5B1 equal to 0 for the sake of consistency of the equations. This is the constraint if the system is to be solvable, which gives us the consistency of the equation. Every column satisfies this constraint, so it is forced on B. So B should satisfy this. We should choose B1, B2, B3 such that this equation is satisfied. Geometrically, we shall see that the vector 5, minus 2, 1, 5 is picked up from here, and minus 2 is picked up from here, and 1 is picked up from here, which are the coefficients of B1, B2, and B3. Coefficient of B1 is 5, coefficient of B2 is 2, coefficient of B3 is 1, and that's what is written over here. In the equation, B3 minus 2B2 plus 5B1 is perpendicular to each column. So one example which will give us B3 minus 2B2 plus 5B1 equal to 0 is B equal to 1, 5, 5. If you substitute this B equal to 1, 5, 5 in this equation, then we'll get 0 equal to 0. We'll get the value of this equal to 0, because B3 is 5 minus 2 into B2 is again 5, that is minus 10, plus 5 into B1, that is 1. So 5 minus 10 plus 5 will give us 0. So Ax equal to B now will be A over here like this, and X like this, and B which is like this one, 155, which we have considered over here. Now by using the elimination method, then we can just try to find out Ux equal to C, where U will be again the same thing which we have got earlier, 1332, 0033 and 0000, X as it is. Now C is 130, which will be straight away corresponding to B1, B2 minus 2B1 and B3 minus 2B2 plus 5B1. And that will be naturally 1, 3, and 0. So if you try to solve this, do this, what you call reduction or elimination for the, so to say, the combination of A and B as well together, which is an augmented matrix, then we are going to get this and this together, this U and this C together. The row gives the equation, 0, 0. The third row rather gives the equation which is 0 equal to 0 as expected, which gives consistency of the original given equation. Okay, here the third row, 0, 0, 0, 0, 0 into U plus 0 into V plus 0 into W plus 0 into Y will be 0 itself, will give us a 0. If this were not 0, then it will become inconsistent, and hence we cannot solve Ax equal to B then. So back substitution of this will give us the second row. If you consider over here, then it will be 0U plus 0V plus 3W plus 3Y is equal to 3. That gives us 3W plus 3Y is equal to 3. And that's what we have over here. 3W plus 3Y equal to 3, and that gives us W equal to 1 minus Y. If you try to solve this, you'll get W equal to 1 minus Y. Similarly, we will have here the first one equation, that is 1 into U plus 3 into V plus 3 into W plus 2 into Y is equal to this value 1. And that is what is mentioned over here. U equal to 3V plus 3W plus 2Y plus is equal to 1. Or if you substitute this w over here, that is w equal to 1 minus y over here, and take this on to the right hand side, then we will get u is equal to minus 2 minus 3v plus y. Now if you substitute the values of u and w in x, so x will be nothing but u, v, w, y. For u, we'll substitute this value. For w, we substitute this value. Then v and y, we keep it as it is. Then we will get these minus 2, 0, 1, 0, minus 3, 1, 0, 0 with v multiplied. Then y multiplied with 1, 0, minus 1, 1. You can check this also. U is equal to minus 2 plus of minus 3v plus of 1 into y. And that is what we have over here. V is 0 plus 1v plus 0y. And that's nothing but v equal to v. W is 1 plus 0v plus y into minus 1, that is minus y. And that is nothing but 1 minus y. Y is nothing but 0 plus 0v plus 1y. This has all solutions of a equal to 0 plus the new particular solution, which is xp equal to minus 2, 0, 1, 0, which is got from here, minus 2, 0, 1, 0. And this two together will just correspond to the solution of ax equal to 0, which we have considered in the last class. This xp is a particular solution to ax equal to b. xp is nothing but the particular solution. The last two terms with v and y yield more solutions. Okay, this will just give us the more solutions because they satisfy ax equal to 0. So ax equal to b can just be solved with the consideration that the complete value of x, that is x complete, is equal to x particular plus x null space. The particular solution is got by solving the equation with all free variables set to 0. That is, in the earlier example, if we set v and y equal to 0, then we are going to get the particular solution over here. And when you multiply the above equation a by a, this equation by a, we will get ax complete is equal to a particular plus ax null space. Ax particular is nothing but b, and ax null space is equal to 0. So if you add b to 0 vector, then we'll get a value b itself, which is nothing but the original equation, which is ax equal to b. Geometrically, the solutions again fill a two-dimensional surface, but it's not a subspace. Why is it not a subspace? Because we have added a particular solution. Because it does not contain the 0 vector. It does not pass through the 0 vector. Okay? Because we have added a particular solution to it. It is parallel to the null space. The null space, please remember that, that will be a vector subspace. But now to this null space, we have added xp, shifting the total thing, the final solution, by the particular solution xp, and hence the final solution will be only a vector subspace, so to say, not a subspace. It will not be a subspace, but a subset. To summarize, we can just say here, if there are R pivots, there are R pivot variables and n minus 1 free variables, then the R value is the rank of the matrix. R turns out to be the rank of the matrix. So here we have R pivots corresponding to R pivot variables. Then definitely the number of free variables will be n minus R, and R will be the rank of the matrix. We get the what you call ux equal to c or rx equal to d from ax equal to b by means of elimination. And if we do that, with R pivot rows and R pivot columns, the rank of the matrix will become R, and the last m minus r rows of U and R are zeros. So if rank of the matrix is R, then we will have last m minus r rows of U and R as zeros. So there is a solution only if the last m minus r entries of C and D are also zero. Rx equal to D and Ux equal to C. So this C and this D should have last m minus r rows in the last m minus r rows to be equal to 0. Then only we can get a solution of the equations specified over here. Otherwise, the solution is not possible. The complete solution is specified by x equal to the particular solution plus the null space solution. The particular solution xp has all free variables 0. Using all free variables as 0, we can find the particular solution. Its pivot variables are the first R entries of D. So Rxp equal to D. Directly we will get from the equation Rxp equal to D the particular solution itself. The null space solution Xn are the combination of n minus r special solutions with one free variable set to the value equal to 1 and all the other free variables made equal to 0. Now, the pivot are not free variables in that special solution can be found in the corresponding columns of R with sign reversed. So, not free variables in that special solution can be found in the corresponding columns of R with sign reverse. What does this mean? We need to go back and see what it means. So you can see that this corresponds to the not free values -3 and 1 in the null space matrix. So this -3 and 1 straight away is picked up as the negative of the 3 over here and -1 over here. 3 and -1 are the negative of -3 and 1. Similarly, the not free 0 and -1 over here are negative of the values over here. The values over here. The values, sorry, over here, 0 and 1. 0 and 1 we have here, and there we have 0 and -1. 0 and -1. So the not free variables in the special solution can be found in the corresponding columns of R with sign reversed. The rank R is very much crucial. It counts the number of rows which corresponds to the pivots in the row space or the number of pivot columns in the column space. There are n minus r special solutions in the null space, and there are m minus r solubility conditions on B or C or D. N minus r special solutions and m minus r solubility conditions on B or C or D. So with this, we come to the end of this lecture. We'll take up the solved example in the next video, and then we'll go to the next lecture.